Hi everyone. So let's look at the properties of these functions and their graphs. So we have y equals 2 to the x in red, y equals 3 to the x in blue, even y equals 1.1 to the x in green. So let's talk about their features. First of all, let's talk intercepts. Y-intercepts. What can we say about y-intercepts here? Well, take a look. The point 0, 1. That magical purple point is the y-intercept for all three of these graphs. In fact, for all graphs for y equals b to the x, where b is nice, the y-intercept will be at 0, 1. What about x-intercepts? Well, turns out there are no x-intercepts. Now, you might be confused about what's going on here. Let me assure you, these graphs are not touching the x-axis. They get very close, but they're not touching. For example, 2 to the negative 10th is very tiny, but it's not quite 0. In fact, on the x-axis, we have a horizontal asymptote, an HA, at y equals 0. Okay, so we have one y-intercept at 0, 1 for all three of these graphs, and we have the x-axis, y equals 0, as an HA for all three graphs as well. Now, what about domain and range? First, let's talk domain. Domain, think x. We pick up every real number as an x-coordinate for each of these graphs. The domain is all real numbers. Now you might wonder, what's 2 to the pi? Well, it is 2 to the 3.14 blah blah. It's a calculus idea. But the domain is in fact all real numbers. The range, however, think y. Well, we're not getting all real numbers. We're only getting positive real numbers. So the range, as you can see here, the range is going to be, we think, the set of all positive real numbers. The range is the set of all positive real numbers. 0 is not in the range. Remember, there are no x-intercepts. Y is never 0 on any of these graphs. 0 is not in the range. Okay, so for all of these graphs, all functions of that type, we have the same features. In general, if b is greater than 1, remember that means we have exponential growth. All right? The graph of f of x equals b to the x, where, again, b is greater than 1, will resemble a j graph. Okay, all these j graphs fall in that category. Basically, y equals b to the x, where b is greater than 1. And we have these as common features for all four of these functions. Okay, so the domain is all reals, right? We get all real numbers as x-coordinates. The range is the positive reals, okay? The y-coordinates we get are the positive reals. The x-axis is an HA. It's a line that these graphs approach, and it turns out they never touch. That's why 0 is not in the range. By the way, in trig, we're going to mention that you're actually not forbidden from touching an HA. So it's not true that graphs never touch their HA, but it's true that for fairly basic graphs, they tend not to touch their HAs. And these guys do not touch their HAs. In trig, however, I'll show you at least one graph that will touch its HA. All right, the y-intercept is at, again, it should be 0, 1. 0, 1. Maybe we can type that in. 0, 1. That's the y-intercept. Remember, we tend to prefer ordered pairs for our intercepts. Okay, so those are the features for f of x equals b to the x, where b is greater than 1. But what if b is, say, 1/2 or 1/3? What happens? All right, well, actually, we could play a little game here. All right, what if b is strictly between 0 and 1? For example, what if b is 1/2? All right, let g of x be 1/2 to the x. This is actually related to f of x, which was 2 to the x. Think transformations. We did this back in 1.4. So if f of x is 2 to the x, don't freak out, but I do want to discuss why this graph's going to make sense here. All right, so observe, f of the opposite of x will be 2 to the opposite of x, and you can actually factor this exponent, and it looks like this. 2 to the negative 1, all to the x, is 2 to the negative 1x. We're reversing the rule that says that when you raise a power to an exponent, you multiply the exponents. But what is 2 to the negative 1? It's 1/2. 1/2 to the x is then g to the x. This guy here, the guy we've been talking about all along. So what's my point here? I'll change the color to really emphasize this. Let's go to blue, all right? So what we have here is that if you replace x with its opposite, all right, you're going to get the guy that we want here, 1/2 to the x. So what happens if we go from the graph of y equals 2 to the x to the graph of y equals 1/2 to the x? What happens? Let's use a different color. Purple. Yeah. Okay. So here, this is the graph of y equals 1/2 to the x in purple. How do we get from the red graph to the purple graph? We reflect it about the y-axis. Remember, when you what we're basically doing is we're going from 2 to the x to 1/2 to the x. What happens when we go from 2 to the x to 1/2 to the x? We're basically replacing the x with its opposite. We're replacing the x with its opposite. When you replace the x with its opposite, when you're looking at y equals f of opposite x, you're reflecting the graph about the y-axis. Hopefully you remember that from 1.4. Now, if this analysis creeped you out, don't freak out. The key thing to remember is that when you're graphing y equals 1/2 to the x, you're getting this guy here, like a curvy L. This is not exponential growth. It is exponential decay, like radioactive decay. What's the idea of radioactive decay? The idea that if you have a radioactive material, like Stewie Griffin from Family Guy, let's say that the half-life of some element is 1,000 years, and you have 1 gram of it right now. In 1,000 years, it will decay to 1/2 of a gram. That's the idea of half-life. The idea being that the element will decay over time and approach nothing. All right, so again, here's the graph of y equals 1/2 to the x. But there are other graphs that look similar. So here's y equals 1/2 to the x. All right, here's y equals 1/3 to the x. Again, it's this curvy L, exponential decay. Okay, even y equals 0.1 to the x, right? Exponential decay. Actually, that's not so surprising. This might surprise you. Y equals 0.9 all to the x. Yeah. Now 0.9, that's a pretty big base relative to these, but still 0.9 to the x, exponential decay. In the long run, you're seeing exponential decay. Even y equals 0.99 to the x, again, exponential decay if you zoom out way out enough. So if the base here, the constant base, is less than 1, even a little bit less than 1, but stays positive, then y equals b to the x will be this curvy L guy. It would be shaped like a curvy L, exponential decay. All right, so in general, if b is a constant, strictly between 0 and 1, then the graph of y equals b to the x will resemble the curvy L graph that we see above. And yet, when you look back at these features that we saw for this previous case here, where b was greater than 1, still, domain is all reals. Range is only the positive reals. I'm going to zoom in. Yeah, I'll just do this here. I'll get a new screen. Okay, y equals 1/2 all to the x. All right, so again, the same features apply. Domain is all reals. The range is the positive reals. We have a y-intercept at 0, 1. No x-intercepts, although we do have an HA at the x-axis, or y equals 0. All right, so actually these same 4 features apply even if b is, say, 1/2. All right. Now some comments about bases that are not nice. What if b is 1? Well, 1 to the x is 1. That's just a constant. That's a flat line. If b is 0, 0 to the x is basically 0, although 0 to the 0 is weird. Again, it's basically a flat line. So these do not represent exponential functions. They're basically constants. If b is negative, we have a real problem, literally. So, for example, this over here. -2, let's say that's our base b, it's not nice. If that's raised to the 5/2, ultimately, because of this thing, the 2 over here, you're taking a square root. And, well, right now we have a problem if we have the square root of a negative number. So this is not even a real number for this value of x up here, the 5/2. So if your base is negative, you literally have a real problem, and I won't mess with you in that sense. So these bases will not give you exponential functions. Now, there is a base that we absolutely love. Our favorite base is represented by a letter. Its name is E. E is, of course, the 5th letter of the alphabet, but it's also a number. E represents a number. It's about 2.718. Both E and pi are pretty close to 3. And like pi, E is also an irrational number. There are various ways of defining E, many ways of defining it in calculus. For example, here's a limit definition for E from calculus. So E is the limit of 1 plus 1 over n, all to the n, as n approaches infinity. In fact, we could try looking at the calculator function here. Okay, y equals 1 plus 1 over, let's say, 10, all to the 10th. Okay, this is of the form y equals 1 plus 1 over n, all to the n, okay, where n takes the value 10. All right, you can see it's about 2.6. What if we make n equals 100 here and here? About 2.7. How about 10,000 here and 10,000, oops, and 10,000 there? All right, about 2.718. So this is very, very close to E. So if you let n approach infinity down here and up here, then this number here will approach E. Again, E is about 2.718. That's pretty much what we're getting here. Now let's consider the graph of y. Well, this is so close to E, we may as well call him E. X of 1, or a 2.718, shall we do that? Oh, graph it, yeah. Yeah, y equals Z, it knows Z. Okay, so that's a constant, y equals a constant. Take a look at this. Y equals this function of n, or x, as the case may be. Graph that. Hey, look at this. As n approaches infinity, right, then the y-coordinates, the value of this thing over here, okay, this whole thing over here, is approaching E. Okay, so this is an HA. Y equals E is an HA for this, as n approaches infinity. That's one calculus definition for E. We love E for all sorts of reasons. A key reason is that the derivative of e to the x is e to the x. By the way, e to the x gives us the natural exponential function, and e is referred to as the natural base. E is our favorite base. In information theory, computers are supposed to be base e, really, and they actually experimented with base 3 computers, but base 2 won the day, binary. Anyway, what about the graph of y equals e to the x? Well, we've seen these things before. Here's y equals 2 to the x. All right, here's y equals 3 to the x. Remember, e is about 2.7. Y equals e to the x. Okay, it's this blue graph that's between the red graph and the black graph. E is just a number. E is just a number. It's about 2.7. So y equals e to the x graphs as a J-curve. All right. Exponential models, that's a fancy way of saying that we're going to attach this constant like a coefficient. Basically, if you remember Norma from Card Sharks, she started off with $200, right? And that's going to be the constant A. In fact, A here represents the initial value, the value of this function rule when x equals 0. If x is 0, remember, this is 1, and then we're left with the coefficient here, 200. So A is going to be the initial value, the value of this when x equals 0. It's the initial value for this function over here. Kind of like time 0. What's the population at time 0? All right, so if b is greater than 1, oh, by the way, let's assume a is positive for now, and b is a nice base. If b is greater than 1, then we get a J graph, and we obtain exponential growth models used in applications such as population growth, like the Malthusian model. And we'll talk about that. Also, compound interest. We'll talk about that in the next video. By the way, Malthus was one known for giving economics the name the dismal science because people were afraid that population would grow exponentially while food supply would grow linearly. That was a big fear. And Malthus was an economist who was concerned about that. If b is strictly between 0 and 1, like if b is 1/2, then you have applications like radioactive decay. Or imagine a store going out of business. Sadly, nowadays, many stores are going out of business. But imagine a store where they're cutting prices in half each week. Okay, then the prices will approach 0 very quickly. So these are exponential models. This is the form of a basic exponential model, and we're going to apply that to compound interest in the next video.